Hi, my name is Taylor McDonald, and I will be presenting my paper titled Reliable Mode Tracking and Gradient-Based Optimization Frameworks with Flutter Constraints. Since Flutter computations require knowledge of an aircraft's aerodynamic, stiffness, and inertial properties, they are typically put off until after the initial detailed aircraft design phase. Delaying Flutter computations, however, can lead to costly and time-consuming redesigns should Flutter be found within the flight envelope of the proposed aircraft. One way to incorporate Flutter computations earlier in the design process is to define the initial aerodynamic, structural, and inertial properties of an aircraft as part of a multidisciplinary design optimization with Flutter constraints. In order to fully constrain an aircraft against Flutter within its flight envelope, Flutter constraints must be constructed for a variety of altitudes and airspeeds. Since these constraints must be evaluated repeatedly for each altitude and airspeed in the context of a multidisciplinary design optimization, they should be constructed in a computationally efficient manner. Frequency domain analyses are therefore preferred over time domain analyses whenever possible for computational efficiency. Additionally, since gradient-free optimization is computationally intractable when large numbers of design variables are used, Flutter constraints should be constructed so that they are continuous and differentiable, so they may be used with gradient-based optimization. In order to construct a continuous and differentiable Flutter constraint, the Flutter speed cannot be constrained directly since the identity of the critical mode may switch from design iteration to iteration. Instead, the stability of each mode in the analysis must be constrained directly, or in other words, the real part of the eigenvalue associated with each mode must be constrained to be negative. Unfortunately, due to the inherently arbitrary ordering of eigenvalues, which result from a linear stability analysis, either on a linear system or on a nonlinear system, linearized about a steady state operating condition. So unfortunately, because the ordering of the eigenvalues is arbitrary, mode switching may occur, which introduces discontinuities into the constraints, because the modes are no longer associated with the constraints that they were originally specified for. A common solution to this problem is to use a constraint aggregation function, such as the KS function, to eliminate all dependencies on mode identity in the Flutter constraint formulation, so that the order of the modes no longer matters. The advantage of this approach is that it eliminates all the discontinuities associated with mode ordering. The disadvantage is that it requires that all modes are treated identically, which may not always be desired. An alternative approach is to use mode tracking to correlate modes from the current iteration with those from a previous iteration. One such method, upon which the new mode tracking method that we present in this paper is based, finds proper mode associations by using the biorthogonality of the left and right eigenvectors. This method uses the left eigenvector matrix from the previous iteration and multiplies it with the right eigenvector matrix from the current iteration to construct, and the mass matrix, if applicable, to construct the correlation matrix. The largest magnitude in each row and or column of the correlation matrix then indicates the best correlation for each mode. Assuming a step size is sufficiently small, the correlation matrix will be diagonally dominant, and a unique mode association may then be found for each mode, assuming a one-to-one relationship between modes exists. In practice, mode tracking based on the construction of the correlation matrix works well, but false mode associations may still occur if step sizes are not sufficiently small. For example, for the plots shown here, there's a false mode association that occurs between a reduced velocity of 1.2 and 1.4, as you can see on the right-hand side in the damping plot. And so to address this issue, backtracking may be used to reduce proposed step sizes if the mode correlations are suspect. In order to introduce this backtracking step in an automated manner, however, we need to introduce a quantitative measure for the accuracy of the mode correlations. To this end, we define the corruption index as the magnitude of the entry of the correlation matrix corresponding to the best correlation for a given mode divided by the magnitude of the entry of the correlation matrix corresponding to the chosen mode, or modes if multiple correct mode associations exist. This measure may be interpreted as the likelihood of a false mode association and approaches zero as the step size is reduced. So our new mode tracking method consists of the following core steps. First, mode associations are determined using the correlation matrix. Then the corruption index is calculated for each mode association. And finally, the step size is reduced if any corruption index is too high. So to demonstrate this mode tracking method, we demonstrate on two systems. One is a linear 2D aeroelastic system, and the next one will be a nonlinear 3D aeroelastic system. So the linear 2D aeroelastic system is constructed by coupling an unsteady aerodynamic model based on Wagner's function together with the typical section model. Now with no mode tracking, the frequencies associated with each mode is really erratic, and so there's a lot of discontinuities that may be introduced into an optimization framework if this was included in an optimization framework. Now if we use the mode tracking method based on just the correlation matrix and no adaptive velocity increments, no adaptive stepping, then for the most part the mode associations are correct, but there is that one incorrect mode correlation that occurs between the reduced velocity of 1.2 and 1.4. Now with the adaptive step size that we introduced in our paper, all the false mode correlation goes away, and also there's additional refinement happens in the areas where false mode correlations are more likely. And we're actually able to reduce the corruption index to an arbitrary low level, and so this allows us to have an arbitrarily accurate high accuracy in our mode correlations. So here's our nonlinear 3D aeroelastic system. Now for this system, with no mode tracking, the motion of the modes are erratic. But if we apply mode tracking with just the correlation matrix, a lot of the modes for the most part are tracked correctly. But if we then add the adaptive step size in, the modes are tracked even better than without it. And we can see by looking at the corruption indices that our mode tracking method is able to reduce the corruption indices down to within the specified tolerance. So in summary, our mode tracking method is able to track modes with an arbitrarily high degree of accuracy. It's applicable to a wide variety of systems, and it's useful for both aeroelastic analyses and optimization.